2 set out upon the water in a simple rectangular boat with mass m is 3,000 kilograms, a length of 3 meters, and width of 2 meters, as shown in the figure below. Part A, calculate the depth of the bottom of the boat y when it floats at equilibrium. The reason that your boat floats at equilibrium is because it is experiencing a buoyant force, meaning that we need to calculate a force problem. And the first step in every force problem is to draw a free body diagram. We'll let that dot represent our boat, and the first force we imagine acting on the boat is gravity of an amount mass times g. The second force that we imagine is the buoyant force. The buoyant force will push upward on the boat, and by Archimedes' principle, the buoyant force is equal to the weight of the fluid displaced. The weight of any object is its mass times gravity. It is not common to refer to the mass of a fluid, since if we tried to do so, we might consider the entire body of water, lake, ocean, whatever, that this boat was floating in. Rather, we like to refer to fluids instead by their density. Since we do need to come up with an appropriate mass times g, we will use the formula density of the fluid times the volume displaced times g, and this is our application of Archimedes' principle to determine the buoyant force. This is a one-dimensional free body diagram, only in the vertical coordinate, and since the object is not accelerating, there's no preference for the plus direction, so we'll choose up since that seems to be the most natural. In this case, the force in the positive direction is density of the fluid times the volume displaced times g, and the force in the minus direction is the weight of the boat, 3,000 g. As always, the sum of the forces is m times a, and the acceleration of this object is 0. Next, we need to fill in the terms of this equation. The first is the density of the fluid, and since the fluid is water, it has a density of 1,000 kilograms per cubic meter. The volume displaced can be understood by examining the figure. The boat itself displaces an amount of water equal to this dashed box. That box has a length of 3 meters, a width of 2 meters, and a height of y. Therefore, the volume displaced will be 3 times 2 times y. The g's will cancel, and we'll get the simple result that y is equal to 0.5 meters. Part B. Oh no! Your boat has a leak in the bottom. Calculate the velocity of water coming through the hole. This is a fluid dynamics problem, and as with all fluid dynamics problems, we'll solve it using the Bernoulli Principle. Returning to the figure, we remind ourselves of the technique by which we solve a Bernoulli problem, and that is, we decide on 2 locations within a single fluid and connect these via the Bernoulli Principle. Since the water touches air at the surface, we will call that location 1. Since we're in a large lake, the velocity here will be 0, and we'll call the location 2 at the bottom of the boat, just as the water runs through the hole. As is conventional in most energy-like problems, we'll set the location of y equals 0 at the lowest point, and so we'll be placing y equals 0 at location 2. We will connect moment 1 to moment 2 through the Bernoulli Principle, which states that the quantity pressure plus a kinetic energy term, 1/2 rho v squared, plus a gravitational potential energy term, rho gy, takes the same value at all points throughout the fluid. We realize a useful equation by setting the location 1 total of these quantities equal to the location 2 total of exactly the same quantities. As with any Bernoulli problem, we have our choice of whether we would like to use absolute pressures, in which case the atmosphere we live in is 100,000 pascals, or gauge pressures, in which we call the pressure of the atmosphere we live in 0. This problem will be simplest in gauge pressures because both location 1 and location 2 are places where the water touches air and therefore has the same pressure as air, which will be a gauge pressure of 0. Location 1 is the surface of the body of water, and this does not have a significant velocity, so we will neglect the kinetic energy term. And finally, since we've called y equals 0 at moment 2, we will have a potential energy term at location 1. This will be the density of the fluid, which is water, times g times the height at location 1, which we found in the previous part of the problem to be half of a meter. At location 2, we still have 0 pressure, since the water again touches the air as it exits the hole, filling our boat. It certainly has a velocity at this point, but this is the location at which we've called the height equal to 0. The density, 1,000 kilograms per cubic meter, will cancel on both sides of this equation, yielding the simple result that velocity at location 2 is the square root of 2g times 0.5, which gives 3.13 meter per second. And finally, we'll calculate the rate at which the fluid is flowing through the hole. There are one of two ways to calculate this rate. The first is density times area times velocity. This quantity is in kilograms per second and is appropriate for both kinds of fluids, gases and liquids. However, in the case of liquids, we consider them to have the same density at all times. Therefore, we calculate the simpler quantity, which is area times velocity, or cubic meters per second. Since our hole is circular, the area will be pi times the radius squared, which can be multiplied by the velocity from the previous calculation to yield a volume rate of flow of water through our hole of 2.46 times 10 to the minus 4 cubic meters per second.